Math 1343, Week 8, Video 5, Goodness of Fit Test, the Critical Value Approach. So far in the videos that we've seen, we built up all the necessary pieces to do a hypothesis test, a goodness of fit test, but we haven't actually done it yet. So let's put everything together, fill in a few missing gaps, and do a goodness of fit test using the critical value approach. Just a reminder, what we're attempting to do is to analyze this sample observation of 256 days distributed Monday through Friday as listed here to see if it is sufficient enough evidence to test the company's claim that this is how the sick days are distributed. And we've got everything we need. All right, so test at alpha equals 5% if the sample distribution of sick days is sufficient evidence to reject the company's claim. The claim that this is how the sick days are distributed. Step number one, as usual, state the hypotheses. Now, we've already done that in a previous video, and I want to remind you what these specific hypotheses were for this particular goodness of fit test. The null hypothesis is all these proportions are correct. So we had written PM for Monday is equal to 25%, so 0.25. PTU for Tuesday was 15%. PW for Wednesday is 15%. Let's put a comma here. PTH for Thursday was also 15%. And, emphasis on the word and, it's important there. PF, the proportion of sick days on Fridays, was 30% or 0.30. And the alternative hypothesis, in terms of the specific proportions, all say not equal to, but have the word or. So PM is not equal to 0.25. P Tuesday is not equal to 0.15. P Wednesday is not equal to 0.15. P Thursday is not equal to 0.15. Or P Friday is not equal to 0.30. Now, that's the numerical way to do it, and it's not necessarily wrong, but it's not very descriptive because it lacks context. All it's saying is either all these proportions are certain values or at least one of them isn't. If you wanted to describe the hypotheses contextually, you could write them in words using some of the same verbiage. For example, the company claims that this is the distribution of sick days. So we could simply say that the null hypothesis is the company's claim of sick day distributions. Should have planned out my space a little bit better. The company's claim of sick day distributions is correct. And the alternative hypothesis would be at least one day's claimed distribution is incorrect. They might all be incorrect. I'll get out of the way in just a second. So contextually, we can say the null hypothesis is the company claim of sick day distributions is correct, where the alternative is at least one day's claim distribution is incorrect. Could be all of them, but the alternative says at least one of them. Which one will I want? Well, which one do you think makes more sense if you were doing statistics for a company? Probably the verbal ones. The numerical ones just drive the math, but the verbal ones really describe what's going on. All right, so there's that, and let's draw a partition line. Here we go. Just while we're at it. Hope I can fit everything in the boxes that I've spaced up here. All right, number 2, calculate the critical value, sketch the regions. Now, if you're doing the critical value approach, this means that you decide if it's a left tail, right tail, or two-tail test, and then come up with the, in this case, chi-squared value that separates the region. So, do you think this is a left tail, right tail, or two-tail test? Well, normally we would look in the alternative hypothesis and look at the symbol there, the relation there. But in a goodness of fit test, this will always be not equal on all of them. So you might think that it's a two-tail test for that reason. But there's something I haven't told you yet. A goodness of fit test is always a right tail test. You don't have to make a decision. This is the first time I've said this, and it's kind of important. So if you're taking notes, and I hope you are, you should write down somewhere that a goodness of fit test is always a right tail test. The reason it's always a right tail test actually lies in the formula for the calculation of the test statistic. Now clearly we're not going to recalculate everything we did in the previous problem, but I am going to go ahead and write the formula. We'll come back to this step in a second. It was the sum of some fractions. The numerator was observed value minus the expected value, and that difference was squared, and then that was divided by the expected value. And in the previous video we did that, and we got 8.6667. So let's go ahead and write that down. But why is a goodness of fit test always a right tail test? Look at the formula and think about what would happen if you did not reject the null hypothesis. And more specifically, think of what would happen if our sample perfectly lined up with the population claim. In other words, what if what we observed exactly matched what we expected? We expect 25% of these sick days to be on Monday. Well, 62.5 of them are. Let's not argue the half-day discussion. But if our sample was in perfect agreement with our proportions from our claim in the null hypothesis, then what we observe would exactly match what we expect. Now, if what we observed exactly matched what we expected, what would the answer to the subtraction problem always be? 0. If your sample perfectly agrees with your population claim, every one of these numerators ends up being 0, which means that your chi-squared ends up being 0. So a test statistic of 0 means perfect agreement between sample and population claim. Recall that the chi-squared distribution is non-negative and starts at 0. So if we were in perfect agreement and had to accept the null hypothesis because our observed data matched it perfectly, then this 0 would have to be in the non-rejection region. So there's no way there can be a left tail over here. Now, as our sample starts to deviate from our population claim, these subtraction problems start getting larger and larger and larger, which means this chi-squared starts getting larger and larger and larger. So if there's too much deviation between what we observed versus what we expected, then this would just get larger and larger and larger. In other words, it would get further and further to the right. So at some point it would cross a boundary to the point where we would say, that's too far, we have to reject the null hypothesis. So a goodness of fit test is always a right tail test. So as a right tail test, we would shade the right tail. The significance level, which was a stated 5%, would still represent the area of the rejection region. Area equals 5%. And the non-rejection region would be the left side. So it will always be a right tail test. Now there's one other key piece of information missing. We need to look up a chi-squared value, but if you recall from the very first video, the chi-squared distribution requires an area to the right, which we have, and a degrees of freedom, which we don't. So somewhere over here, I need to put what the formula for degrees of freedom is. So we'll throw an asterisk there, and we got some room up here, and here's the asterisk. The formula for degrees of freedom is k minus 1, where k equals the number of categories. Or the number of proportions we're testing. Because each category has a proportion. Because we're testing 5 proportions, k is equal to 5. So in this example, this example, k equals 5, so our degrees of freedom will be 5 minus 1, which is 4. It's a pretty easy calculation. You just have to remember that k is the number of categories, which is always the same as the number of portions that we're testing. All right, so we go to the 4 degrees of freedom. We look up 5%, and I'm not gonna move my camera just so you can see my chi-square distribution. In fact, I don't even have a chi-square distribution pulled up. So if you give me 1 second, I'm pretty much there. I'm practically there. Click here, and voila. And we'll leave this open so that it will be there for the next one. Open up, there we go. All right, so if you have the chi-squared table and go to the 4th row for 4 degrees of freedom and go over to the 5% column, which is the, it's a couple past the middle. 4th row, 5% column, I see a value of 9.488. 9.488. That's our critical value. If our test statistic goes beyond that, it lands in the rejection region. Just remember, the degrees of freedom is k minus 1. K is the number of categories, which is the same as the number of portions being tested. And it's always a right-tail test. We've already done step 3. That was the previous video. We calculated the test statistic. It's 8.6667. And in standard critical value approach, we make our decision by locating our test statistic relative to our critical value, and it falls just a little bit to the left of it. So it was a large test statistic, but not too large. So it lands in the non-rejection region, and therefore our decision is do not reject the null hypothesis. And let's answer the question. Well, there was never really any question asked. You can tell because there was no question mark. But we were asked to test if the sample distribution is sufficient evidence to reject the company's claim. Well, the company's claim was the null and we didn't reject it. So we can answer the question by saying the sample was not sufficient evidence. The sample was not sufficient evidence to reject the company's claim. The sample was not sufficient evidence to reject the company's claim. We blame the discrepancy on the particular sample that was picked and not necessarily that the company's claim was incorrect. Now, I almost considered doing a 10% significance level. And think about what that might have done. If this were 10%, we would need a bigger tail, which would push the critical value further to the left, and there might have been a possibility that then we would have rejected. I'm just curious. Had we used a 10% significance level, the degrees of freedom would have still been 4, and our critical value that separates the regions would have been 7.779. So just as an interesting side note, had this been a 10% significance level, we would have actually rejected the null hypothesis. In the next video, which will be the last one about goodness of fit test, we're going to do one more goodness of fit test from beginning to end.